Good morning, everyone. My name is Anand Padmanabhan, and I'm a research associate professor in the Department of Geography and GI Science at the University of Illinois Urbana-Champaign. And I want to welcome you to this VCO session for iGuide. VCO stands for Virtual Consulting Office, and it is being conducted by iGuide, which is the Institute for Geospatial Understanding through an integrative discovery environment. We do this VCOs on a regular basis, like on a weekly basis. And you can see today's VCO topic as well as kind of upcoming VCO topic. And we also have a mailing list down there, so you can sign up for our weekly insider or a quarterly newsletter or whatever, so you can keep informed, excuse me, about the happenings in iGuide and what we are doing. So you will get notified about all the upcoming VCOs as well. So please consider signing up using that QR code. So with that, I want to introduce today's VCO. The topic today is the extraction of geospatial and climate attributes for large-scale hydrographic modeling. And our presenter is Mohammad Galib from Purdue University. He is a PhD student working with Professor Venkatesh Marwade. And their research is contributing to iGuide as well as to other efforts at Purdue. So join me in welcoming Mohammad, and I'll pass on the virtual Zoom stage to Mohammad. Thank you.
Hello, thanks, Professor Anand, for this wonderful introduction. So, shall I share my screen?
Yes, please.
Is that visible?
Yes.
Okay, great. Hello, all, good morning. So, today I'm going to talk about extraction of geospatial and climate attributes for large-scale hydrologic modeling. So, this is the brief outline of our today's talk. So, these are some of the agendas that we're going to go through. So first of all, we'll be having some introduction about large sample hydrologic research, and then what are the current challenges that we are facing for in large sample hydrologic research, and what is our framework basically addressing those challenges or limitations, and then especially what's the iGuide's role in doing that. And then we'll also have a quick walkthrough through our framework that we have basically for automating all those things. First of all, so basically the large sample hydrology refers to the analysis of hundreds and thousands of catchments, and where we are using consistent data sets and methods, which basically enables us for comparative study in hydrology, as well as to come up with some generalized hypothesis for in terms of like hydrologic research. And also we are developing a lot of data-driven models, like deep learning, machine learning models out of that. For example, this is a map which I have taken from one of the study, the CAMELS data, which basically published the CAMELS data, which is kind of the benchmark in large sample hydrologic research. So, which includes more than 600 catchments, and then a catchment and their data sets, like basically attributes, and then hydrometeorological time series data. Further introduction of the CAMELS-like data. So CAMELS stands for Catchment Attributes and Metrology for Large Sample Studies. So it was first published in 2017 by Ador et al. So it's kind of first comprehensive data set for large sample hydrologic research, which includes more than around 671 catchments across the entire US. And it basically has two parts. So one part includes the attributes, catchment attributes, which are like more than 60 attributes over there, and covering different classes and categories like topography, climate, soil, vegetation, geology, and hydrology. And then second part is the time series data, which is like basically the model forcing data or hydrometeorological data. And then it's one of the widely used for comparative hydrology and model benchmarking. I think hundreds of studies are being done like using this data set. So further introduction of the camels, like nowadays people are kind of like working upon in part of like generation of camels like data in multiple countries. So this is the original paper or original article basically, which is for US, and then people are coming up with for different countries, like this one for Denmark, camels like data for Denmark, like this is for Switzerland, camels like data for Switzerland, and then for Great Britain and for India, recently we have CAMELS-like data set for India. So, but the current bottleneck is that if somebody wants to generate CAMELS-like data for their custom study area, so this is the kind of the challenge that we have. Can we generate CAMELS-like data set or the attributes for our custom study area? Because the existing data sets are limited to those predefined catchments. So can we extend that for our own study areas and for our own custom catchments? So which basically requires a lot of manual processing as well as is time and effort consuming. So that's why we need to come up with something which is reproducible and scalable, as well as something automated workflows in order to kind of like generate such kind of data set. So here comes our framework, where basically we are addressing these objectives. That is to develop automatic framework for extracting camel-like dataset, which supports basically as of now, our framework is supporting just a USGS, any USGS gauge catchment. And then also we are like some of the base data sets which is not available on cloud platforms. So what we are doing, we are using the platforms like iGuide, special thanks to iGuide. So where we are integrating the iGuide platform basically for hosting those kind of data sets. And then we are for purpose of reproducibility and the community accessibility, we are using cyberfaces to host those Jupyter notebooks. And further, we have also kind of like created a Python package, which kind of like automatically can create camels-like dataset for any USGS gauge catchment. So first of all, as part of our framework, we are fetching the dataset from the original data, which is being hosted either in cloud platforms, or if it's not available on the any cloud platform from where we cannot access that using Python code or anything. So then what we are doing, we are using iGuide platform basically to host the data set on the iGuide cloud platform. And then we are hosting those codes or scripts, basically the Jupyter notebook on cyberfaces, which is again community accessible. I mean, anybody can access them. We'll have a walkthrough as well. And then we have also created this camel setters kind of this is Python package which is basically can create camels-like data set for any USGS gauge catchment. So again, the iGuide is basically playing here the role for hosting one of the important data set as part of our from where we are creating those attributes. So which is like GLiM and GLHYMPS data set. So GLiM refers to global lithological map and GLHYMPS basically global hydrogeology maps. And then we are sort of like redistributing using by a Python package, again, a pygeoglim is another Python package, so which we have created. So basically to redistribute the data and also automatically kind of create those attributes which are related to this geology data. Let's have a quick walkthrough. So basically on the cyber faces, how can we access those Jupyter notebooks and how can we kind of like create the data set as well as this camels setters Python package. So here is the platform we have, and if we navigate basically to this learn page over here and then take the course, so it will land you to this page, and here you can just click on like the second course, and it will further navigate you to these Jupyter notebooks that we can use basically for creating the camels-like dataset. Like I mentioned already, we have two parts as part of the CAMELS-like dataset. One part is the catchment attributes. So as part of this one, we are creating more than 60 catchment attributes. And then second part is basically to aggregate hydrometeorological time series. So these both kind of data, it kind of like combines, and if we combine both of them, it's like the complete CAMELS-like data. And we are using this kind of data set for a lot of like data-driven modeling. So because we have limited amount of time, so I won't be kind of running these cells like this notebook. Rather, I'll be just having a quick walkthrough, like with into like an entire notebook. And because if we run all these cells, it will take a lot of time. So first of all, here we have the required libraries. So these many libraries we are using basically, which also include our pygeoglim. And this CTIML, this kernel basically already contains all these libraries. These are basically pre-installed over there. So we just have to run this cell, and you're just like all of the libraries will be loaded over there. Then we are creating required directories over there. And then first part is basically the watershed delineation. So we are getting the watershed for our catchments from USGS and LDI. So here, first of all, we have to do the gauge selection. So which gauge site we want to work upon. So let's say over here, if somebody is like selecting this example, like these are the gauge IDs 010311500. So Huckett IDs if you have some knowledge of that. So we are selecting over here the gauge IDs of particular catchment, and then after that, running that. So it will be kind of like we'll start working on that particular gauge, and then here the next cell basically will delineate the watershed and also create some metadata related to that. So when we run this cell, so it will basically delineate the watershed for that particular gas that we selected, and then also give you some metadata related to that catchments, like the name of the catchment and the area, location, all those things. The next is once we have the watershed shapefile, now we can create the attributes related to that catchment. So next part is to create topographic attributes. So the attributes which are related to topography, like elevation, slope, etc. So these are some of the attributes that we'll be extracting out of this. And here we are using basically the base data is USGS 3-depth DM data. So if we run this cell, then it contains everything from helping functions and all. Then finally, execution part. So it will first of all start downloading the DM data, which are required for that particular area, the region of interest we have. And then we'll start computing all of the attributes like slope and everything. And then finally, it will give you the topographic attributes and also give you some map is showing the DEM for that particular area we considered, and also the slope for that particular area. Next part is to create attributes related to climate, or basically the climate indices. So here, these many attributes basically we are creating over here. And then we are getting the climate data basically from GridMet daily climate data. So we have also provided the timestamp. You can change this timestamp if you want to have. And then this is the function basically we are using. And then after that, after running all these cells, finally, so we have various helping functions over here. And then after that, after we run the final cell, so it will start fetching the data from the GridMet. And after retrieving the data, so it will start computing the climate indices. And it will give you finally the attributes related to climate we have. So almost like 10 to 15 indices we have. Similarly, we can create the attributes related to soil characteristics for that particular catchment. And here again, we are accessing the data from the data, which is like Polaris and GNetSco data. And we are using here basically a facility provided by Microsoft, which is like Microsoft's planetary computer. So they are providing a stack API, basically the API from where using which we can get the data using the Python code. So this Polaris and GNSCO data we are fetching, and then we are creating these attributes out of that. So these are some of the attributes that we are doing. So if when we run these functions, these helping functions, so they are basically doing all of the things from fetching the data to creating all of the attributes. So finally, after running this is kind of the output that you will expect out of this. First of all, it will extract the data set, and then it will start working upon creating those attributes. So these many attributes we will be getting, which includes like water capacity, field capacity, sand fraction, and all. Similarly, the next part is to create the vegetation related attributes. And here we are basically using satellite data like MODIS and like NLCD data. So again, we are using for this basically are fetching the satellite data using Microsoft planetary computer. So basically they are hosting that. And these are some of the attributes that we'll be extracting out of that: leaf area index, green vegetation fraction, and all like various attributes related to those vegetative indices. So using that data and these helping functions, Python functions, if you run this cell, so finally you should be able to get, we have multiple cells. So you should be able to get for that particular gauge those attributes. First of all, it will connect with the planetary computer and extract the satellite data, fetch the satellite data, and then we can also change the timestamp, by the way, over here. So we have multiple options over here. And then it will finally give you the vegetation, so the attributes related to vegetation. And then geological, the attributes related to geology, geological characteristics, basically. So here we are using our pygeoglim Python package, which again, basically using iGuides platform for hosting the GLiM and GLHYMPS data over here in order to extract these many attributes. So using that GLiM and GLHYMPS data, which is being hosted over the iGuide platform. So, and then pygeoglim Python package. So we are kind of like getting these attributes over here related to geology. Similarly, I think the last part is the hydrological signatures. So for these hydrological signatures, these are basically the signatures or the attributes we will be computing, which includes like flow statistics, base flow index, runoff ratio, and all. These are kind of like some of the important hydrological signatures. And then here we are using this for stream flow data. We are using USGS and NWIS daily discharge data, and for precipitation, the grid data. And using that, we have multiple helping Python functions over here. And then after doing that, a lot of functions over here. And then finally, first of all, it will start extracting the data. And then after that, it will kind of create those attributes. The next part is finally kind of integrating all those attributes that we have created so far, and then exporting those attributes so that we can, which are kind of like model ready. So in such formats like which are model ready. So here, basically, I'm considering two formats. One is the CSV format, another one in JSON. And then also exporting the metadata related to all those attributes, kind of like information related to all those attributes we have. So this is the cell basically doing all those things. And then after running this cell, we should be able to get an integrated catchment attributes dataset for that particular catchment, like for this gauge ID 0.0103150. And then you should be able to see that data over here. So this is the CSV form. So right now we just did for one gauge ID. And so here is the same, basically all of the catchment attributes related to that that gauge ID. So all those attributes that we can see over here. And then further, we can also do the results validation. So basically what I'm trying to do, I took this particular gauge ID is also a part of the original CAMELS data. So that's why I'm able to do the results validation. So we can also do that. So here I'm fetching the original CAMELS dataset for that particular USGS gauge ID. And then I'm doing that. So these kind of these are some of the absolute differences that we are getting for some of the attributes. So then why we are getting these kind of like differences for those particular attributes, because we are using some different data for this one. Like these, most of them are related to topography. These attributes related to topography. So as part of this module or this framework, we are using the latest DM data that is being provided by the USGS. And then original CAMELS data was using the previous version. So that's why we hope that it's like better than the earlier one. And most of the rest of the kind of, we can say the attributes are kind of like almost same. So we can also extend that for multiple basins. Like we have an option for doing that. Let's say we are providing a list of if we provide a list of catchments, let's say these are the gauge list we have, we can also provide kind of like a text file of the list and then work upon this one for as many as you want, like number of gauges you want. And then it will create you and finally give you the data for that. So now if we come to the second part is basically to aggregate the hydrometeorological time series data, which is kind of like a forcing data for hydrological modeling. So second part, we are using these variables, basically fetching all of the data from the GridMet. So these are the variables that we are using. So precipitation, maximum temperature, minimum temperature, radiation, vapor pressure, all those things. Then again, we have the libraries there that are already being like installed in this CTAI-ML kernel. So, and then once you run this cell, so it will load all of the required libraries from there. And then again, we are doing, this is the function basically to create the watershed shapefile. Again, same thing we are doing over here. And then fetching the climate data from the GridMet. So these are the helping functions, basically. Multiple helping functions we have. And then finally, to create some summary plots for the data set that we have. And this is the main execution function. And then finally, after we execute that cell, so it will give you the basically, first of all, fetch the watershed shapefile, and then fetch the data set, the climate data set for that. And then it will also create some kind of like the graphs, the variation of the data sets, let's say the temperature over here, over this temporally from 2010 to 2020. So we can basically customize the timestamp as well over here. So the precipitation, so here we have the data for the precipitation, and it's also creating like for precipitation and PT, the graphs as well. And then we can also do some analysis part, rest of the part, like related to all these data sets. Water balance check we can also do. So multiple things we can do after that. And then we can extend that for, again, for multiple USGS gauges. So we can provide some list over here. And then you can, like at one time, you can create for multiple gauges. So this is finally the CSV file that you should be able to get after this is kind of like, we can say, the model ready. So you can train any data-driven model using all these data sets like that you should be able to get. So now this is kind of a lengthy process, but just to make it easy, so we have also created a Python package. Okay, so this is the second part. So it's kind of a black box, but this one is the detailed one, the Jupyter notebook. So here we just give some command. We just give some command. So it's pip installable. So in any device, you can basically install this one using this command, pip install camel setters. And then you can start working upon them. If you just give these kind of commands, so basically, we have two options. One is the pip installable, and another one we can work upon this with the command line things. So here also I have provided some example or basically example uses so that you can utilize to how we can work upon this one. So you can explore this package basically how we can work upon this one and do whatever we did so far within few commands only. So this is the brief overview, and this one is kind of the pygeoglim that where basically we are using the iGuides platform to host the data, and using this pygeoglim we are basically accessing the geological data which is required for attributes creation. So this is the package which includes the Python API to fetch the data over there. Okay, great. So these are kind of like the future directions. So we are again working upon this one for expansion to including other data sets, data sources, as well as global level beyond the CONUS region. And we are also trying to integrate some other data sets as well. Then we are also working upon functionality enhancement over there so that we can support custom watersheds like other than USGS cages. And then we are also working upon the attributes as part of this research. And we'll do some other like uncertainty quantification for the attributes. We'll be adding those things as well. Here is the community contribution. Basically, we are sort of like open to collaboration. So that how can we build a community-driven attribute library? So how can we enhance, and also I need some suggestions if you have any, and how can we make this kind of a very robust kind of package or kind of workflow for like further enhancement. So these are some of the resources we have if you want to go through, and then you can contact me over here. This is my email ID, and you can also see the links for kind of like the data sets and everything. These are some of the references, and thank you. Thanks for your patience. If you have any question, you can ask.
Thank you, Mohammed. Any questions for Mohammed?
Hi, Mohammed. Asmita here. It was great presentation.
Thank
I
you.
just wanted to know, like, what is the resolution of the data set you shared? Spatial
So
resolution and temporal resolution.
so so it's basically like I showed you, we are getting the attributes from different data sets which have different kind of like resolution, like the base data sets. And we are trying to make them focus to that particular catchment only. So basically we are doing averaging for that particular catchment that we are concerned about. So that's kind of the methodology which is being used in multiple papers like the original CAMELS data sets and all.
So suppose I have a spatial resolution data with the spatial resolution 9 kilometer, and I
Mhm.
don't know what is the area of your catchment. So are you downscaling, upscaling, and also which method are you
So
using for averaging?
so averaging, I'm using upscaling basically. Basically what I'm doing. So let's say we have the catchment, and we have let's say we have the resolution 9 kilometer resolution, all those, let's say we are taking the precipitation data with 9 kilometer resolutions. And then what we are doing, kind of doing basin averaging. Okay, for the entire basin, we are just doing the averaging and then getting this one value out of that.
Okay, so like for your entire catchment, you'll be having 9 by 9 mini tiles and you're averaging them.
Yes.
Okay. So this is suppose 9 by 9 is one tile and your catchment area is more than that.
More than that.
What
So then we
what
are
if
doing
your
averaging.
catchment area is less than what the resolution you are getting in that case?
Okay, so I have also included the buffer as well. I mean, let's say if you have the catchment area less than the resolution we have, so we have option in the codes to add the kind of, in that case, add some buffer to the catchment area so that whatever whatever the next grid it captures, basically we can take that.
Okay, that's it.
Yep.
Thank you.
Thank you.
Sorry. Any further questions for Mohammad?
Hello.
Yeah.
Yep.
Yeah, thank you for the great presentations.
And one more. Could you please just go back to the links slide you shared? I just wanted to take a screenshot.
Yeah, sure.
Can I proceed?
Yeah, sure. Please go ahead.
Yeah, I will start from the last questions. If your catchment is smaller than the grid size, and you said that you provide the functionality to add buffer and then get the average of that. So did you try to use like nearest neighbor or anything? Because in my opinion, adding outside grid to your catchment could add a little errors to the calculation. Thank you very much indeed.
Perfectly. First of all, that's a great suggestion. We can use algorithms like nearest neighbor. But the thing is, for especially as of on this, how can we improve that? So as of now, we didn't get any catchment, which is basically so small, like USGS gauge catchments. Basically, we didn't get any. We didn't face any catchment, which is basically so small that the resolution of the data set which we are using, it's kind of like more than the catchment area. So, but yes, definitely we can include that, like adding buffer, as well as we can employ some algorithms like nearest neighbor, basically, to capture the data.
Thank you. Any further questions? Okay, I have one. Mohammed, you shared the notebooks. Is that something also can be attached to this data set that you have on the platform, and can be directly used? So
Sure.
that could be something. I know you have on the CyberFaces platform as well. So is that something usable by people?
Yeah. So I can, sure, I can attach that to the basically on iGuide platform as well. And the CyberFaces platform is basically anybody can use that. So it's also, and I mean, you don't even need to use your own resources. So it's basically you'll be using to run these notebooks, the resources of CyberFaces. And definitely I'll provide the link for here in iGuide platform as well.
Okay, sounds good. Thank you. Any further questions for Mohammad?
Mohammed, I have just one question actually to start with.
Yeah, sure.
You mentioned a grid. This grid is based on USGS dataset, or is it something like arbitrary that you do, or just might have missed the whole concept of the grid?
So the grid I was mentioning, basically it was related to the particular data set that we are using. Let's say there is graded data, precipitation graded data. So the grid will be the same with the original data set is basically providing us. So it's not like any grid I'm providing. So I'm just doing averaging, like basin averaging, I would say, or catchment averaging to get the data as a single value out of like multiple spatial data sets.
And that's based on lat long kind of grid, right? It's just the
Yes, perfectly.
geographical.
Perfectly. Yep.
I see. And you didn't face any data set that had a coordinate reference system that was different from your original grid, right? Like could be like I don't know, a local
Yes.
points that might not be in the same coordinate system
hmm
that you have.
Yes, we do. That's basically the main kind of, I would say, um, that's kind of like which takes a lot of effort while working manually upon all those things. That's why. So all those codes basically they are doing, they are kind of like doing that, matching the coordinate systems as well. Like we are working just in single coordinate system. If some other, if any data set is basically different, has different coordinate system, then we are kind of like again converting them to our working coordinate system using the codes only. So yeah,
And
obviously,
that's part of your code, or
yeah,
it's
that's
you
part of my
mentioned
code.
it's manual, or is it
That's part
manual?
of my code. No,
Oh, you
nothing is
part of one
manual. So
you.
that's the beauty of this workflow. So nothing is manual over here. So within the codes, it's already there.
I see. So you ask for the user to identify, let's say we want to reuse your algorithm, right? The
hmm
workflow that you mentioned. So
hmm
do you ask the user to provide a specific metadata regarding the data sets that he wants to incorporate, or like your code asks for a specific parameters? Like I'm just trying to imagine, because reuse is a challenging process, right? Yeah, you have to capture all the metadata for the new person who is not familiar with your code.
Yeah,
So
okay. Basically, it's very simple. Kind of, you just need to provide the only thing user has to do is just to provide its custom USGS gauge site. That's only one has to do. Otherwise, rest of the thing is it will automatically, do. So here, the gauge selection, here, there is only the input which is required from the user. So they just need to provide the gauge ID, particular gauge ID they want to work upon, and then rest of the things it will take care.
I see. Okay,
Yep.
thank you.
Yep.
One more thing here, I would like to add, like, what is this gauge ID?
Okay, so
It's related to catchment.
actually, yes, it's related to catchments. So USGS is basically these gauges where the USGS is basically providing you the discharge data. Okay, so they
Mm-hmm.
have particular gauges actually. So around more than 9,000 gauges we have throughout the US. And then on those particular gauges, so they are basically monitoring the runoff data.
Mm-hmm. Okay.
Yes.
So it doesn't work like latitude, longitude, no, right?
As of now, yeah, that's kind of part of the future work that instead of using just the gauge IDs, so can we provide the lat long and then start working up, create the catchment attributes. So the main problem with that is if we are working upon any lat long is that, so we don't have runoff data for that particular point.
Mm-hmm.
So
Got it.
that's the only problem we have. So we are still working upon this one. Figuring out how can we make this one for any lat long, and in fact, like for any watershed throughout the globe.
Yeah, thank you.
Thank you. Any further questions we have? Again, Mohammad, thank you for the presentation, and the link to the
Thanks.
recordings would also be available online. And we have a bunch of VCOs that are coming up. So these VCOs are held on a weekly basis. So please register and join to them. There is a, let me give me a second. Yeah, if you can view my screen, you can see the upcoming session and a QR code down there for iGuide mailing list, so you can sign up and get notified for all the future VCOs. So again, thank you to Mohammad, and again, as I said, we'll make the audio, the recordings available on the iGuide website.